Scene script. Have you ever pondered over the mysteries that lie beyond the night sky? Ever wondered about the difference between a black hole and a white hole? Welcome to the fascinating world of cosmic phenomena, where we'll delve into the intriguing and enigmatic nature of black and white holes. Start by imagining a black hole, a region of space where gravity is so strong that nothing, not even light, can escape its pull. These beasts of the cosmos are formed from the remnants of massive stars that have collapsed under their own weight. Inside a black hole, all paths lead to a singularity, a point of infinite density, where the laws of physics as we know them cease to exist. Now let's flip the script and consider a white hole. These are essentially the theoretical opposites of black holes. Instead of sucking everything in, a white hole spews out matter and energy. But unlike their black counterparts, white holes haven't been observed in nature. They exist purely in the realm of mathematical equations, a solution to Einstein's field equations of general relativity that has yet to find a corresponding reality. Now you might be wondering, how can a white hole, something that ejects matter, be a solution to the same equations that give us black holes, cosmic vacuum cleaners that suck everything up? Well, that's the beauty and mystery of the universe. It's a place where opposite extremes can be two sides of the same coin, where time can theoretically run forwards and backwards, and where the very fabric of space and time can be twisted, stretched, and warped in unimaginable ways. In the following scenes, we'll take a closer look at these cosmic wonders, discussing their formation, their properties, and their implications for our understanding of the universe. We'll explore the event horizons of black holes, the absence of such in white holes, and the paradoxes and mysteries that surround these celestial bodies. Dive with us into the depths of space as we unravel the mysteries of these cosmic phenomena. Scene script. Black holes, the monstrous devourers of the cosmos. But what exactly makes them so formidable? Let's dive into the abyss to understand these cosmic beasts better. At the heart of a black hole is a concept that often leaves even the brightest minds scratching their heads: the singularity. This is a point of infinite density, where our conventional understanding of physics and space-time breaks down. Imagine squishing the entire Earth down to the size of a marble. That's the kind of density we're talking about. But how do these astronomical oddities come to be? The birth of a black hole is a tale of celestial catastrophe. When a star significantly larger than our sun exhausts its nuclear fuel, it can no longer withstand the inward pull of gravity. The star implodes, causing a spectacular supernova explosion. What's left behind is an extremely dense core. If this core is massive enough, the force of gravity overwhelms all other forces, causing it to collapse inward into a single point, creating a black hole. Now you might be wondering why the name black hole? Well, these cosmic entities have such strong gravitational pulls that nothing, not even light, can escape their grasp. This makes them practically invisible, hence the name. Surrounding the singularity of a black hole is a boundary known as the event horizon. This is the point of no return. Once anything crosses this boundary, it is forever lost to the black hole's insatiable hunger. And the closer something gets to the event horizon, the stronger the gravitational pull. This makes black holes the ultimate cosmic vacuum cleaners, sucking in everything that ventures too close. But black holes are not just cosmic monsters. They are also key players in the life cycle of the universe. Their immense gravity helps shape galaxies and drive the evolution of the cosmos. Just as interesting as their birth is their insatiable appetite for devouring everything that crosses their path. Now imagine a cosmic object that is the exact opposite of a black hole. Welcome to the realm of white holes. Just as black holes devour all matter and energy that venture too close, white holes are theorized to expel matter and energy. They are the theoretical time reversals of black holes, a concept that can be a little mind-bending. Picture a movie of a black hole played backward. You'll see matter and energy emerging from a point in space, right? That's essentially the concept of a white hole. Instead of an event horizon that nothing can escape from, a white hole would have an event horizon that nothing could enter. The possibility of white holes comes from the mathematics of general relativity, Einstein's theory of gravity. In these equations, both black holes and white holes appear as solutions. However, while the formation of black holes is well understood as the end state of dying, massive stars, the formation of white holes remains a mystery. Some theorists have proposed that white holes might be the other end of black holes, creating a bridge or wormhole through space-time. Matter and energy fall into a black hole, get churned around in quantum weirdness, and then spit out a white hole. However, this scenario faces a significant problem: time. In the physics of black holes, time essentially stops at the event horizon, but in a white hole, time would have to run backward, a concept that's not supported by our current understanding of physics. Another challenge with white holes is that we haven't observed any. While black holes have made their presence known through their gravitational effects on nearby objects and the detection of gravitational waves, white holes remain elusive. Yet, despite these challenges, white holes continue to intrigue theorists. They offer a tantalizing solution to some of the paradoxes and problems in our understanding of black holes and the wider universe. White holes, then, are the cosmic spitballs, ejecting matter rather than consuming it. The event horizon, a point of no return. But how does it differ in black and white holes? Well, in a black hole, the event horizon acts as a boundary, a line that once crossed, there's no coming back. It's the point where the gravitational pull becomes so powerful that not even light can escape its clutches. It's the ultimate cosmic roach motel, where everything checks in, but nothing checks out. On the other hand, a white hole is entirely different. It's like the mirror image of a black hole. Instead of an event horizon trapping everything, a white hole has a reverse event horizon that pushes everything away. Nothing can enter a white hole. It's a cosmic repellent, if you will. So, while black holes are cosmic hoarders, white holes are the ultimate in social distancing. While black holes trap everything within their event horizon, white holes forbid anything from entering. At the heart of a black hole lies the singularity. But what about white holes? We've all heard of black holes, those celestial vacuum cleaners that suck in anything that gets too close, including light. The singularity at the center of a black hole is where everything it swallows up ends up. This singularity is a point of infinite density, where all the matter gobbled up by the black hole gets squeezed into. It's like a bottomless pit, where space and time themselves come to a grinding halt. But what does this mean for our understanding of space-time? Well, in the realm of a black hole, the normal laws of physics start to break down. Near the singularity, space becomes infinitely curved, and time, as we understand it, stops. It's like you've reached the edge of the universe, a place where our normal understanding of reality doesn't quite apply. But then what about white holes? These hypothetical cosmic objects are the exact opposites of black holes. Instead of sucking everything in, they spew out matter and light. But do they have a singularity at their core like black holes? Interestingly, the answer is no. Theoretically, white holes lack a singularity at their center. Instead of a point of infinite density, a white hole has a region of zero density. It's like an endless fountain, where matter and light are emitted, but nothing ever goes in. This lack of a singularity in white holes has profound implications for our understanding of spacetime. If a black hole represents a point where spacetime ends, then a white hole represents a point where spacetime begins. It's like a cosmic birthplace, a point where matter, energy, and even time itself are born. So, while black holes crush matter into a singularity, white holes lack such a point. This contrast between black holes and white holes, between singularities and non-singularities, gives us a fascinating glimpse into the mysteries of the universe and the nature of space-time itself. The existence of black holes is widely accepted, but what about white holes? We've delved into the depths of black holes and journeyed through the speculative realm of white holes. Now let's address the elephant in the universe. Do white holes actually exist, or are they just figments of our mathematical imaginations? In the realm of theoretical physics, white holes are indeed possible. They are solutions to Einstein's field equations, just like their black counterparts. But while black holes are a widely accepted part of our universe's landscape, white holes remain largely theoretical. There's a key reason for this. While black holes are formed from gravitational collapse, a process we've observed in the universe, white holes would require a reverse process. This would mean matter being expelled outwards, something we've yet to observe on the cosmic scale that a white hole would necessitate. But absence of evidence isn't necessarily evidence of absence. Some scientists suggest that white holes might be hiding in plain sight. They could be masquerading as certain types of supernovae, or perhaps they are at the hearts of quasars, those incredibly bright and energetic objects at the centers of some galaxies. Others have proposed that the Big Bang itself was a white hole, spewing forth all the matter and energy that makes up our universe. This is a fascinating idea, but it remains just that, an idea. It's not backed up by any direct evidence. Despite the lack of concrete proof, the existence of white holes is a tantalizing prospect. They represent a perfect counterbalance to black holes, offering an elegant symmetry to the universe. If they do exist, they could potentially answer some of the most perplexing questions in physics. So while we continue to search for definitive proof, white holes remain at the edge of our cosmic understanding. They are a frontier waiting to be explored, a mystery waiting to be solved. The existence of white holes remains a tantalizing question, one that continues to puzzle the brightest minds. We've explored the intriguing worlds of black holes and white holes, but what sets them apart? Let's dive into the heart of the matter. Fundamentally, the formation of black holes and white holes is markedly different. Black holes are formed from the gravitational collapse of a massive star, creating a point in space with infinite density, known as a singularity. A black hole's gravitational pull is so strong that nothing, not even light, can escape its grasp once it crosses the event horizon. Conversely, white holes are purely theoretical entities. They are the time reversals of black holes, spewing out matter and energy instead of sucking it in. If they exist, they would be characterized by a repulsive force that prevents anything from entering. Unlike black holes, white holes don't have an event horizon or a singularity, making them fundamentally different in structure and behavior. The concept of an event horizon is another major differentiator. In black holes, the event horizon marks the point of no return. Anything that crosses this boundary is forever trapped within the black hole. White holes, on the other hand, theoretically lack an event horizon. Instead, they would have a sort of reverse event horizon from which matter and energy are expelled, but nothing can enter. Singularities are another point of divergence. At the center of a black hole lies an infinitely dense singularity, a point where all known laws of physics break down. In contrast, white holes lack a singularity. They're believed to be regions of space that are repelling rather than attracting matter. Then we have the existential debate. While black holes have been observed and their existence is well accepted, white holes remain purely speculative. They exist in the mathematical solutions of Einstein's equations, but we have yet to find any observational evidence for them. These contrasting characteristics make black holes and white holes some of the most fascinating entities in our universe. The study of these cosmic phenomena continues to challenge our understanding of the universe, opening up new frontiers in our quest for knowledge. Our journey through the cosmos brings us to the end of this intriguing exploration. We've traversed the depths of black holes and the hypothetical frontiers of white holes, two of the most fascinating phenomena in the cosmos. We've touched upon the basic concepts, understanding the gravitational properties of black holes and the theoretical nature of white holes. Both these entities are solutions to Einstein's field equations in general relativity, yet they are as different as night and day. Through our cosmic journey, we've witnessed the birth of black holes born from the collapse of massive stars. We've explored the conditions that lead to the creation of a singularity and an event horizon, the boundary beyond which nothing can escape a black hole's gravitational pull. In contrast, we've pondered the formation of white holes, the reverse of a black hole collapse. Unlike black holes, white holes lack an event horizon and a singularity, making them theoretically intriguing but observationally elusive. We've delved into the fascinating concept of time reversal, where white holes are considered the time-reversed counterparts of black holes. We've also discussed the intriguing phenomenon of Hawking radiation and the absence of it in the case of white holes. Our journey has not been without paradoxes. We've faced the information paradox associated with black holes and speculated on whether white holes could provide a resolution to this cosmic conundrum. We've also explored the challenges in observing and detecting these cosmic entities and the theoretical connection between black holes, white holes, and wormholes. We've even delved into alternate theories that might provide different explanations for these phenomena. In this vast cosmos, white holes remain speculative, their existence yet to be proven. Yet they hold the potential to dramatically impact our understanding of the universe. So as we conclude our journey, I encourage you to delve deeper into these captivating astrophysical phenomena. Remember, the universe is full of mysteries waiting to be unraveled. Keep wondering, keep exploring.